question that Gina had was about homework. So class 9 homework, which we would have done last Friday if we didn't have a snow day, is today. So today we're doing class 9. It will not be on the first exam as originally planned. It will be on the next exam. And so the homework for class 9 will not be due on Friday because Friday is your test. So class 9 will be due on 2/24, okay? And then Mondays will be 2/26, and we'll just do that whole routine all over. The absolute final deadline for all of the homework in the next section will be the date of the second exam, which right now is 4/2. So if you don't complete all of your homework by the due date, then you have that 20% penalty as long as it's done by 4/2. So I just keep changing that final absolute deadline to be wherever your next exam is on your schedule. Speaking of which, I will also have a new schedule for you on Friday. I've actually got it done. It's sitting at home in my printer, and I forgot to pick it up this morning, but I figured you had enough stuff to do anyway today. So this pink sheet is what Caitlin and I put together. This is actually a discussion forum as part of our online class for Math 107, and we thought it would be a really nice study aid for all of you. This comes from this idea of doing something like this comes from a Writing to Learn Mathematics book that I have, and we actually just changed it into this format. So this really takes care of all of the equations that we've done in chapter 1, and notice linear inequality and inequalities involving fractions or factors. It says NA for test 1. We're not doing those. Also, I should have put right up here under absolute value equation, you can also put NA for test 1. You're not responsible for these for test 1 because absolute value equations we're covering today. I just forgot to put the NA test 1 up there. Okay, so you're welcome to use this page if you want on Friday and put notes on the back, or you can bring in a blank piece of paper with whatever notes you want on both sides. It's totally up to you. The test covers all of chapter P and all of chapter 1 up until class 8, which is the first part of 1/6 that we covered last Wednesday. All right, so if you still have not done P2, P3, P5, I strongly urge you. I did notice that I went in and looked at your homework that a lot of you had gone back and done the homework for P2, P3, and P5, okay? So let's take a look at today's material. So let's start us off, Austin, with equations in quadratic form.
Today we're going to continue our work with a special category of equations.
It should say R right in there. I gotta fix that. R quadratic. Okay, so what I want you to do is I want you to look at the right-hand equations in the right-hand column and the equations in the left-hand column and see if you can find a pattern that allows us to say these are quadratic in form. Actually, that one is quadratic. This is a quadratic equation. The one above it and the one below it are quadratic in form. So what is it about looking at these equations and then looking at a typical quadratic equation, whatever that means, but a quadratic equation that has all three terms? What is it that puts these in quadratic form? And I'll give you a hint. X to the 4th minus 10x cubed plus 9 equals 0 is not in quadratic form. So in other words, I made something sort of like that one, almost like this, almost like. And this is not quadratic in form. So look at these equations and see if you can come up with a pattern that if I gave you an equation What pattern would that have to have so I could put it in that left-hand column? Talk amongst you and put your flags down. And when you think you have a couple of ideas, put your flags up and we'll talk about it as a class, okay? It would be easy for me to just like tell you, right? I'm just trying to get you to see. Okay, I'm just trying to get you to see if you can see the pattern, because when you're looking at these and you don't know what class you're in or what part of the book you're in, right? You're going to have to know how to recognize what the heck kind of equation you have so you can pull out a strategy to solve it. So often it's much more useful if you can find the pattern than if I just tell you what it is, okay? Now, I'm not going to let us struggle for 20 minutes. If we can't come up with a pattern as a class, then I will prompt you and lead you to the watering hole, okay, so to speak. So what did table 2 come up with? So you're telling me how to solve it, right? Or how you think you would solve it versus the pattern. So that's what I'm sort of looking for. So you're noticing something, Seth. I'm just trying to, you're saying that this, if you took the square root, if this was just x to the 4th, because we couldn't take the square root of each term, that's not allowed. But if you took the square root of just x to the 4th, you notice that it's half of this one, right? Or you could say that this power here is twice that one, right? And you're noticing that if you went from x squared to x, it's half, right? Because when you take the square root, it's the 1/2 power. So you're chopping each one in half. So that's what you're saying. Okay. So Seth is noticing that if you looked at, and this is terminology, the degree of this term, the degree. So this equation has 3 terms. Here they are. The terms are the individual pieces of an addition and subtraction problem. So many students confuse the word terms with factors. Terms you get when you add and subtract stuff. Factors you get when you multiply. So we have 3 terms here. The degree of the first term is what? What's the degree of the first term right here? The degree. To the 4th power. Degree, recall, was the exponent. The degree of the equation is the highest exponent or highest power. The degree of the term is whatever your exponent is. So the degree of the first term is 4. What's the degree of the second term? 2. And this one's a little tricky. What's the degree of your constant term? If it were 1, it's a good guess. If it were 1, it would look like this, 9x. That has degree 1 because there's a 1 on that x. So what could we put beside that? What power could we put for x so that it would equal 9? 0, because anything except for 0 to the 0 power is 1. So we could write 9 like 9x to the 0, but boy, that would be writing a lot, right? So a constant term, every constant term has degree 0. Because 9 could be written as 9 times x to the 0. So this has 0. Okay, so let's move our way over to this quadratic equation. And now I'm just going to move this little box down for a minute. So here are my 3 terms, x squared minus 10x and 9. Tell me what the degree of each of those 3 terms are. What's the degree of x squared? What's the degree of negative 10x? 1, because now it's x to the 1. And the degree of 9? 0. Okay. 2, 1, 0, 4, 2, 0. Let's move this up a little bit. Ooh, I didn't want to move that up. Okay, let's move this down again. What's the degree as we go across here? 2, 1, 0. Degree as we go across here? 2, 1, 0. Okay. So you can either say that the degree of my first term is double the degree of my middle term, right? Or you can say, as I move left to right, I divide by 2, right? 2 by 2 gives me 1, 1 divided. No, I can't say that because I don't get 0. But what you can notice is that the relationship between your first term and your second, the degree, is a 2 to 1 ratio, or a 1 to 2, depending on which way you're looking at it. Look at here. 4 to 2 is a 2 to 1, or to go from right to left, you say I'd multiply 2 by 2 to get 4, 1 to 2 relationship. Okay, so does that hold true down here with my very last equation? 5x to the 2/3, 11x to the 1/2, and 2. Let's see, what's the degree of my first term? What's the degree of my first term here? Right here, what's the degree? 2/3. What's the degree of my second term? 1/3. And my last term is constant. That has to be there. You have to have a 0-degree term in there, or else it's just polynomial. And then you can just factor out a greatest common factor. All right, unless it has fractions for exponents. All right, does this have the 2 to 1 relationship? Is the degree of the first term twice the degree of the second term, the middle term? So that's what you're looking for, that pattern. The pattern being the degree of your first term is twice the degree of your middle term, and your last term is a constant. That's quadratic in nature. So let's see how we would solve an equation that was quadratic in form. I'm going to show you 2 ways to do it. You pick your favorite way. If one of them is more confusing for you, you can just turn off and daydream. All right? So if I saw an equation like this, I'll show you how I would solve it. Okay? And I'm not going to solve it like this monster table that I have here for you. If I saw something like this, is that what the equation is, or I got it backwards? 10x and the 9, okay. Thought I had it wrong. 10x and then the 9 here. If I saw something like this, and it's because of the strategy I'm going to show you in a minute, what I see is something equal to 0. So in my mind, I say 0 product principal. Can I factor this? And I don't get all wigged out because it doesn't say x squared minus 10x plus 9, which is what you're used to factoring. I say I can factor that. What are the factors of 9 that add up to 10? 9 and 1. So I just factor it like this. I put my 9, my 1, my 2 negatives, and the only difference is instead of it being x minus 9 times x minus 1, what's the value of my first term in each binomial factor? That's a mouthful. X squared, right. That's the only difference. Oops, there should be a 0 over here, right? Now I do what I've always done. The only difference is instead of each factor that you set equal to 0 being a baby linear equation, it's going to be quadratic. So I have x squared minus 9 equals 0, and I have x squared minus 1 equals 0. And to solve this, to avoid the temptation and forgetting one of your solutions, you remind yourself 2 answers. So I should get 2 different factors when I factor each of these. They're the difference between squares. So those are the nice, easy ones to factor. They're just conjugates of each other. X plus 3 and x minus 3 are conjugates of each other. There are my 2 answers for the first factor, plus and minus 3. And here are my 2 answers for the second. Notice how many solutions do I have altogether? 4. What was the degree of my original equation? 4. Okay? Always gives you a little like heads up so you don't miss half of your solutions along the way. If you were writing this in my math lab, just remember they want you to put it as a solution set. You start with your smallest number and you work your way up to your largest value of your solution. Okay? That's how you would write it. Now, the method that your book shows you is if you don't recognize or feel comfortable doing this, they have you turn it into something that looks like a quadratic by doing a substitution. It's called U substitution. U substitution is used quite a bit in calculus, and so it's kind of nice to introduce it now. So again, you have to recognize the pattern that your first term, x to the 4th, is squaring your middle term. That x to the 4th is when you square x squared. Once you recognize that, You know you're in this pattern of being quadratic in form, so you do this thing called U substitution. You say, I'm going to let U equal x squared. And when you do that, x to the fourth becomes x squared squared. And since this is equal to U, we can say x to the fourth is equal to U squared. So this becomes U squared minus 10 times U plus 9 equals 0. So the U represents x squared. So if in your mind you go back here and you put an x squared in everywhere you see that red U, you would be back to your original equation. Now, why do we do this? Because when you look at this, you know how to do this. You recognize it as quadratic, so you can solve it. So you now use your principal product, I'm trying to talk too fast. Your zero principal, I can't even talk, zero product principle to solve this. You say, okay, I'm going to take my left side and write it as 2 factors that equals 0. And I'm going to set each factor equal to 0. And solve each one, just like I've done a zillion times before. The problem is you're not done. Why not? Why can't I just circle that and go on my merry way? Huh? Not here because I don't have any squares in this one. That's the difference. I only have 2 solutions and I know I need 4. We're almost getting there. This equation solves for U. What's our original equation? Right, my original equation is in terms of x, right? So I haven't done all my work yet. I've solved for U, but now I have to substitute. What is U equal to again? X squared. So now I just go underneath each one of these and say U is x squared. And now this is where you want to do your plus and minus. Okay, so you can do it just like we did at the beginning. You could subtract 9 from each side and set your quadratic equal to 0, which is really how I encourage you to do these. So you do not forget that this is plus or minus 3 and this is plus or minus 1. There are your 4 answers. Okay, so some of you may not need to use this U substitution if you can happily look at this and say, oh, I can factor that just like I did here. The difference is here your factors are quadratic in nature. They have second degree. Here your factors are linear, and then you go back and make them quadratic. Okay, so those are your 2 choices. All right. Anybody have any questions on either method, either the idea behind it or what you would actually do? All right, so let's take a look for a minute just at this. I'm not going to solve it. I'm not going to solve it. If I gave you an equation like this on a test, tell me truthfully, how would you approach solving this? What would you do intuitively? You would just simplify it by doing x plus 3 times x plus 3 plus 7x plus 21 minus 18 is 0. You'd use your distributive property there. Then hopefully you'd multiply this out the correct way and get this, right? And you would just do all of this, right? Oh, right. And then you'd put all your like terms together. Oop, I only got 1x squared plus 13x. And what do I got here? 9 and 21 is 30 minus 18. So what's that? Minus 12 is 0. So far, I haven't done anything wrong. And then you'd factor that, right? And you'd get x minus 12, x minus 1 equals 0, x equals 12, x equals 1. Fine, no problem. Okay, so why are you showing me another method? Just because I can. And just because it may help make it easier. If it doesn't, do this out the long way, because this is not quadratic in nature. This is a quadratic equation, but we're not used to seeing the thing that gets squared as an expression. We're only used to, our eyes are only used to seeing it as a single letter like X or W or Z. So I'm just showing you that you can make this look like the quadratic you're used to by using this u substitution. You let u equal what here? What might be a good thing to let u equal? Right, the expression x plus 3. So now everywhere you see x plus 3, you put a u in, like that. So now it becomes u squared plus 7u minus 18 equals 0. And now you factor this. What are the factors of 18 that differ by 7? What are the factors of 18 that differ by 7? 2 and 9. U plus 9, u minus 2 equals 0. Now you have it as a 0 product. You take each factor and you set it equal to 0. You know, we know this game by now, right? And you solve for u. But our original equation was in terms of x, so all you do now is you go back and you replace u with what u equals. U is equal to x plus 3, so you replace u with x plus 3, and you keep the rest of your equation exactly the same. And lo and behold, all you have left to solve now is two baby linear equations for x. So now you get x equals negative 12 and x equals negative 1. Ooh. Oh, it's supposed to be plus. No, see, I would have gone back and found my error because these two are supposed to equal each other, right? So 9 and 21 is 30. 30 take away 18 is plus 12. So that's my error, plus 12. So this should have been a plus, this should have been a plus, and therefore my answers would have been both negative. They've got to be the same answers. I'm solving the same equation. So what? Scroll up. Okay. So that's u substitution. Okay. Now, I want you to try this on the next problem, and don't let the fact that it's got rational exponents make you get nervous. You just use your substitution. I'll help you out. Put your flags up. Put them down now, and then put them up if you need help. See if you can do the next one on your own. It's a little harder, but we'll also give you a good review for solving rational exponent equations for Friday's test together, because as I said, we have a long class today. So I think we're able to work through the fact that the u substitution, we look for our middle term, which is x to the 1/3, because when we square x to the 1/3, we multiply our powers and we get x to the 2/3, which is going to be u squared. So u equals x to the 1/3, and we rewrite the equation by replacing x to the 1/3 with a u wherever we see it. So this becomes 5u squared plus 11u plus 2 equals 0. And now we're searching for factors of both 5 and 2 that add up to 10. So 5 times 2 is 10. And then we're left with the 1 and the 1. So that's plus 1 plus u plus 1u. Now we set each of these equal to 0, like we've done throughout the lesson today. And we get, after a few steps, we get u equals negative 1/5. And after one step here, we get u equals negative 2. Now, the only difference between this and all the other ones we've done is when we put in what u is equal to, we're going to get a rational exponent, right? A rational number exponent, which is what we learned how to solve a zillion years ago, because it was before all these snow days and holidays, and it probably feels like it was a zillion years ago, right? So we have an equation like this, x to the 1/3. What does the 1/3 say to do to x? What is another way of saying what 1/3 means in another language? What did you say? X cubed to what? What did you say? All right, so you're telling me how to, all right, you're telling me the strategy for solving it, which, hang on for like 30 seconds, but what does x to the 1/3 say? cube root of x, right? And we know whenever we solve an equation, we undo by doing the inverse. So some of you in some of your minds may like to write that like this. The cubed root of x equals negative 1/5, and that's okay. And how do you undo it, Dan? You got to cube both sides, right? Okay, so whether you put it in radical notation or you keep it as exponents, when you have a power raised to a power, these two powers are reciprocals. When you multiply 3 times a third, you get 1, which is beautiful because that's what you're after. And now you cube the numerator and you cube the denominator. Negative 1 cubed is negative 1 times negative 1 times negative 1, which is negative 1. 5 cubed is 5 times 5 times 5, which is 125. You do the same here. You cube both sides, and you get x equals negative 8. Okay, so those are your two solutions. You always go back and check them. All right. So that's a little review of rational exponent equations, which you will see one of these on your test Friday. All right. So you make sure you get some type of little notation on this little study aid sheet that I've given you for how to solve those. Okay. Yes, you could solve this using the quadratic formula, but just remember you'll be saying u equals. So you'll still get u equals negative 1/5 and u equals negative 2. Yes, it will still work that way if you couldn't factor it. Absolutely. Good question, Dan. Okay, so let's see what's coming up next. Okay, absolute value equations. And I think I'm just going to skip this first part and take you into the more difficult ones, just because I'm looking at the time and I want to make sure you have plenty of time to get to your group activity today. But I think that if you look at the absolute value of x equals 3, and we don't do it with a graphing calculator, if I gave you this equation to solve, my first question to you is, how many solutions does this equation have? Absolute value of x equals 3. 2, okay? Because x, which is the stuff inside that absolute value, think of that thing as just saying stuff. The stuff inside could be either 3, or the stuff inside could be what? Negative 3, because once you take the absolute value of 3, or once you take the absolute value of negative 3, you're going to get 3. So all you do is you drop your parentheses, you drop your absolute value symbols, and you turn this into two equations. And you do that by dropping. You literally just drop those symbols, the symbol for absolute value. And what you have left is the stuff inside. And there's my stuff inside. My stuff is called x. And I can say my x could either be a positive 3 or my x could be a negative 3. Okay? And if you were to graph this, I'm just going to put it over here. You can also see the video from the first class. The first class didn't do the 5 to the 2/3, the one we just did, but we did do this out. So so here's the graph right here. I thought it would be more important to work on that equation with you than actually doing this. So here is how we would do this graphically. We would take the absolute value of x and we'd set that equal to y1. So that would be this V looking picture right here. This is the absolute value of x, and y2 is this constant equation, y equals 3. So it's just a horizontal line. And where these two intersect are negative 3 and 3. That's the solution. That's the x values. Because we know the y values for both of these points. We know the y value is already 3 because we're on the line y equals 3. And we get two values of x that bring us to 3. So those are the common solution. So the x coordinates are plus and minus 3. Okay, and this is how you do it. All right, so here's how you can use, this is a strategy that we use for solving any absolute value equation. Notice your absolute value is isolated on the left side, and you have something in between, some expression. It could be as simple as x, or it could be 10x plus 5 inside there. It doesn't matter what it is. It's going to equal c, c being a positive number. And to solve this, you literally drop your absolute value symbols and you set the u inside equal to c or its opposite. And that's the strategy you use to solve all absolute value equations. So let's take a look at this first one. All right, we have the absolute value of 2x plus 1. So the stuff inside is called 2x plus 1. So you drop your absolute value symbols and you write 2x plus 1 twice. Okay, and if you want, you can just sort of do two arrows like that to remind you. Okay, so the 2x plus 1 that's inside the absolute value symbols could either be the same as the number 11, because the absolute value of 11 is 11. So I want to see what value of x is going to make this equal to 11. Or the stuff inside the absolute value symbol could be what number? Negative 11. So you say, what value of x is going to make this be negative 11? And then you just solve these linear equations in the format you always use. And you get 5 for the first one. And for the second one, you get 2x equals negative 12 and x equals negative 6. And you're supposed to check them, but I'm going to tell you that they both work to save a little time. Okay? So notice, in order to use this method, your absolute value term has to be all by itself on one side and your constant is on the right side, or vice versa. It doesn't matter what side it's on. So isolate the absolute value. Okay? Notice, I did not try to solve this absolute value until I dropped the symbols. Do not try to solve this as long as those absolute value symbols are there, because you'll only get one answer. All right, if you try to say subtract 1 from both sides right now. All right, let's take a look at one that requires a few more steps. How about this one? So what's the main problem with this? I have the 3. Anything else, Brittany? So I have the 3 in front of the absolute value, and what else do I have? I have the 4, the term 4 hanging on, being added to it, right? So in order to isolate the absolute value piece of this, I have to do 2 steps. I have to undo the adding of 4, and I have to undo the multiplication by 3, right? So in order to isolate, we want to isolate this on one side of the equation. And in order to do that, we have to undo the addition of 4 and undo the multiplication by 3 on both sides. So let's do that. We're going to undo the addition of 4 by subtracting 4 from both sides of the equation. And now we're going to undo the multiplication of 3 by dividing both sides of the equation by 3. Now I have my absolute value term isolated on one side, and now I solve it and say, hey, all that stuff inside, all this stuff, could either be equal to a positive 7, or all that stuff inside could be equal to a negative 7. Now I have 2 baby linear equations to solve, which are absolutely no problem. You'll get x equals 4 here, and x equals negative 4 there. Oh, negative 3. Okay. Okay. So you all know how to solve linear equations, and all you had to do was just isolate that and then separate your 2 equations. Any questions on this at all? Okay, the last thing we have to cover is how to solve a linear inequality. Okay, and a linear inequality, when you solve a linear inequality, your answer is an entire solution set. It's an infinite number of solutions. So we're going to come up with a new way of writing a solution set other than set builder notation, which I think a lot of you have already shown me that you're just not that comfortable with it. So think about this sometime between now and Monday, number 8. Just put over here. Think about it. I'll ask you on Monday. So solving linear inequalities, we want to introduce to you a new way to write a solution set. So how could we represent the solutions to this inequality? Can someone read me this inequality? What does this inequality say as you read it left to right? Brittany? X is any number less than or equal to 7. How many numbers do we have less than or equal to 7? A lot, right. So we have to have a way to represent a lot of numbers. We can't sit down and write them down because the minute we take the first, I don't even know what the first number is that's less than 7. And don't say 6, like someone in my other class did, because we need to forget our idea that numbers, solutions are just integers. There's a zillion numbers between 6 and 7. Okay. So first of all, how would we represent this inequality? And that's a real mathematical way of saying it, a zillion numbers, but it gets the point across. Okay. I remember when I was little and I used to count, I'd get to a zillion pretty quickly. So x less than or equal to 7. You play hide and go seek and you go 10, 20, 30, 40, 50. Do you remember that? Isn't that a great way to do multiples, right? All right, anyway, stop. How do I represent that solution set, x less than or equal to 7, with the real number line? Well, that's what I'm asking. Closed dot right because of the equal to. What do you say? You agree, right. Absolutely. Solid dot, and where do I put it, Brittany? On this 7, yep. And then a big arrow all the way to the left forever and ever and ever. All right. So set builder notation, I'd have to do all this. That represents the set of all x such that, and then you throw that inequality right in there to the right. That's set builder notation. So today we're going to learn a more convenient way to write this, and it's called interval notation. And in interval notation, this is what that same set would look like. So let's talk about this. So interval notation, your largest number goes, in this particular case, would go on the right. Notice I have this fancy bracket here. And to me, that looks like a staple in a staple gun because I'm attaching the number 7 to this solution set. I'm including it. So there goes my staple because I'm including 7. And as I go to the left, there is no smallest number. It goes forever and ever like the universe, right? Unless you're really into astronomy and you go beyond the black holes and all that stuff, which just my mind can't really comprehend. So anyway, so here we say we go to the left forever and ever. We're going towards negative infinity. That's what goes in the first spot because that's smaller than 7. Any number to the left of 7 is smaller. Your smaller quantity goes here. But because negative infinity is not a number, you can't include it, so you put an open parenthesis. So this is interval notation. Right? I'm going to give you some practice with this for like three opportunities coming up right now. So here we go. Here's another interval right here. 2 brackets with a 2, comma 3. This is an example of what we call a closed interval. It means the same thing as this in set builder notation. The set of all numbers x such that x is between 2 and 3, including 2 and 3. So if we were going to represent that on a graph, graphing it on a real number line, someone want to tell me how to do this? Cambry, can you tell me how to represent that on a number line? Closed dot at 2, closed dot at 3, yep. And then what? Everything, yep, everything in between. There it is. That's how we would graph it. How would we write it in interval notation? We just did right there. That says the same thing. We have 2 brackets because we're including 2 and 3, so we're stapling them down as the endpoints. 2 is your smaller number, that goes first. 3 is your larger number, that goes second. and you put a comma in between. All right. Now the next type of interval is called an open interval because we're not including the -1 and 5 as part of our solution set. So this, okay, so as set builder notation, we'd say the set of all x such that x is greater than -1 and x is less than 5. So to graph it, how would I graph this? Can you help me out with this one, Connor? Which kind of 5? Yeah. Yep. And then what would I do? Yep, just squish, 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 squish. All right. All right. So notice we have parentheses. Now this one is neither closed or open. It means the same thing as all x such that x is less than or equal to 1 or greater than or equal to -4. So CJ, can you help me with this one? Graphing it? Yeah. Yep. And everything in between. All right. When we have intervals that involve either negative infinity or positive infinity, just remember that whenever you're using negative infinity or positive, you must have parentheses, either before the negative infinity or after the positive infinity. These are called infinite intervals. Okay, so why do we use interval notation? Because we have to learn how to solve linear inequalities. So let's do that right now. I want you to solve these two inequalities at your seat and tell me what you discovered. There's one difference between solving inequalities and solving equations. So you could think of this as 3x plus 3 equals 0 and -4x equals 8 if you want, but there's going to be one rule change, one notable difference between solving these as an equation and solving these as inequalities. So at your seats, work these out together, see if you can agree, and then we'll discuss them in like 5 minutes. Okay, so what interval represents the solution set for the first inequality? Could someone tell me the interval that represents the solution set for the first inequality in A? Yep. Yep. And the number line looks like this. And that's set builder notation. So solving the first inequality didn't involve anything different than solving the equation, right? Okay, so no problem here. You just solve it, all right? What was the one notable rule change that's different when you're solving an inequality versus an equation? What was the one thing that you have to keep in mind? What's the one difference? Nobody noticed any differences? Okay, well, tell me how you did the part B then. All right, so you did change something, right? If we were solving this as an equation, just like an equation, we wouldn't change anything, right? We would just divide both sides by -4, and you'd get x is less than -2. Well, that doesn't work. So you take any value of x less than -2, like -5, for example, and you throw it in. -4 times -5 is 20. 20 is not less than 8. You have to reverse the direction of your inequality. That's the only difference between solving an inequality and solving an equation, is that whenever you multiply or divide both sides of the inequality by a negative number, let me write that out a little clearer, by a negative number, you must reverse the direction of your inequality symbol. Okay, so when I divide both sides of this inequality by -4, bing, 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 the fire alarm goes off. You get x here and you get -2. That's not any different, but this must be reversed. in order for your answer, your solution set to work. So it's -2 all the way to positive infinity. So it's open parenthesis, -2, infinity, parenthesis. Now if you pick anything in this set and you plug it back into your original equation, your original inequality, the left side will be less than the right side. Yep. Because if I put -2 in here, Gina, -4 times -2 is 8, and that's not less than 8. It's equal, and I don't have my equal sign. Yep, when it's included, right. It's stapled on. Any other questions? All right. I want you to have 10 minutes to work. I'm going to save this one for a minute. When you have a compound inequality, you'll see these on your homework. This inequality you can write as a single inequality like this. You can just take the x minus 4 and say it's less than or equal to 1 or greater than -6. So you can just make it into one inequality with two sides. It's called a compound inequality. And you can solve it either individually. You could do each one of these individually if you want and get your answer. Or you could just solve this by doing what you would normally do to solve for x. You'd add 4, but just remember to put it on both sides of the inequality symbol. You'd add 4 here, you'd add 4 here, and now your answer is x less than or equal to 5, x greater than -2. So as an inequality, I'd have -2, 5, and what would I put on the side of the 5 there, Gina? What kind of symbol? The bracket, right? Okay. Back where? Yep. Yep. Okay, so you got less than 10 minutes. I would encourage you to save 2 minutes longer so you can finish or get really close to finishing your group activity. It should take about 10 minutes.